Hey there and welcome to this video. Today we'll implement the GPT or Generative Pre-trained Transformer from scratch. To be more specific, we will try to replicate the behavior of an existing model from the wildly popular Transformers library of Hugging Face. It is implemented inside of this modeling GPT module, and this is the actual class. Anyway, to be able to fit everything into a single video, we are only going to focus on the forward pass. That means that we are not going to implement any training logic. Plus, we will make other simplifications since the goal is to create a minimal working implementation. Once we are done, we will just download a pre-trained model from the Hugging Face Model Hub and copy manually the weights to our custom model to see how it performs. Anyway, this video is purely educational, and I guess you should probably be using Hugging Face for any real use case. At the same time, their implementation is, in my opinion, very complex since it covers the training logic, parallelization, and many other things, and one can get easily lost in it. Also, our implementation is going to be very much based on this amazing repo by Andrej Karpathy. And yeah, as always, all the credit goes to the authors and the contributors of the aforementioned repositories and also to OpenAI. I'm not affiliated with any of them in any way, and I apologize in advance for potential misunderstandings and bugs in my code. I hope you enjoy the video. I prepared a couple of slides to explain the most important concepts. First of all, let me try to explain what the main goal of the GPT is. The model takes in text as input, and then it generates a new token that represents a plausible continuation. And we can use a simple trick to actually generate text of arbitrary size, which is called auto-regression. We just take the single token that was generated in the previous iteration and we add it to the end of our input text and then just simply rerun the GPT model. And we can do this for as many iterations as we want. Now let us look at the forward pass without delving into details. As discussed, this video is only going to be about the forward pass in the context of inference. And at no point we will discuss the training. Anyway, let's say that our input text is today we are. And first of all, we will give this text to a tokenizer that is going to split it into 4 tokens. And what is really important is that these 4 tokens exist in a vocabulary and have a unique index assigned to them. The tokenizer itself is not something we will discuss in this video, and we will just use an existing Hugging Face implementation. The sequence of 4 numbers representing the 4 tokens then continues to what we will call the GPT module, and I will describe it in detail in the next couple of slides. For now, let me just stress that it outputs a probability distribution over all tokens in the vocabulary. And the higher the probability of a given token, the more plausible it should be as a continuation of our input text. Note that this is different to what I mentioned in the previous slide, where the GPT model was spitting out a new token right away. I just wanted to make things simple. In reality, it does indeed give us a probability distribution, and it is up to us to decide what, let's say, sampling strategy to use to generate the new token. Anyway, now that we have an understanding of the general pipeline, let us focus on the GPT module. Note that in the following slides, I will completely leave out dropout modules and some normalization modules since they don't change the shape of tensors, and I don't want to clutter the slides too much. Okay, so this is the first part of the explanation of what is happening inside of the GPT module. As discussed, it inputs the token indices generated by the tokenizer, and these token indices are then dispatched to 2 different embedding modules. First of them is the token embedding, and the second of them is the positional embedding. Note that I call them modules, however, in the background, they are nothing else than a single 2-dimensional tensor, and by running a forward pass on them, we simply query rows of these tensors. The token embedding module basically holds 1 learnable embedding for each token in the vocabulary, and the positional embedding has 1 learnable embedding for each position the token can have in the input text. And finally, we just take the token and the positional embeddings and we element-wise sum them together, and we are done with the first part. Our tensor then goes through multiple so-called decoder blocks, and I will talk about the decoder block in the next slide. However, the most important fact to point out is that the shape of the input tensor is identical to the shape of the output tensor. Then we continue to linear module. What is actually happening is that we have a single linear module that is reapplied independently to each and every token, or in other words, a row of the tensor. And the output dimension of the linear module is going to be the vocabulary size. And then we will simply discard all the rows except for the last one. And then we feed this last row of logis corresponding to the token R through the softmax, and we will end up with a probability distribution. Note that at training time, we wouldn't discard any rows. However, yeah, again, we just focus on the inference. Anyway, the final probability distribution is exactly the one we are going to be using to determine what the next token could be. Let us now zoom into the decoder block and try to understand what is going inside of it. The input tensor has a shape, number of tokens times number of embeddings. And first of all, we run it through a layer normalization module, and note that similarly to the linear layer we have seen before, we actually reuse the same layer normalization for each token. The output tensor has the same shape as the input tensor. Then our tensor continues to the mask self-attention module. The resulting tensor is then summed with the very initial tensor, or in other words, the first row of this diagram is a residual block. Then again, we apply layer normalization, and finally we apply a multi-layer perceptron. Again, we sum the result of the residual block with the starting tensor. And yeah, that is our decoder block. Let us now have a quick look at the mask self-attention module that we saw inside of our decoder block. First of all, this slide is only going to show what happens if we have a single head. Anyway, we take the input tensor and we feed it through a linear layer. What is special here is that the linear layer will have 3 times as many output features as input features, and that is why its output can be thought of as 3 separate tensors of the same shape as the input. These tensors are called value, query, and key. And now the idea is that for each row of the query tensor, we want to compute a probability distribution over the rows of the key tensor that will represent how similar a given query token is to a selected key token. And this probability distribution is created by computing inner products and normalizing them with softmax, as you can see in the formula. There is one crucial restriction, and that is that we apply a no look-ahead mask. That means that if we take, for example, the third query row, we can only compute how similar it is to the first, the second, and the third key row, and we manually set the similarity to the fourth key row to be 0. This mask will prevent us from including information that is contained in the future tokens in the embedding of the current token. Anyway, once we have this probability distribution, or we can also call it attention weights, for every single row of the query tensor, we then simply use them to compute linear combinations of the rows of the value tensor, and we end up with a new tensor that again has the same shape, number of tokens times number of embeddings. And finally, we feed it through a linear layer, and that's it. Anyway, now we should have all the necessary, let's say, theoretical knowledge, and we can start coding. All right, so let us implement the neural network. And first of all, we will just start with a small technical detail, let's say. Maybe you remember the decoder block had an MLP inside of itself, and one of its layers, let's say, is going to be the Gaussian error linear unit activation. And we will just outsource this implementation to what Hugging Face transformer has. We can also use the inbuilt torch one, but they seem to be slightly different. And I just want to make sure that at the end, our forward pass gives us exactly the same results for our implementation and the official Hugging Face one. Now let us actually do something real, and that is the implementation of the decoder block. First of all, we choose the dimensionality of our embeddings, and then we specify the number of heads for our multi-head self-attention. Number of positions represents the maximum number of tokens we can have, and this block needs to have this information because we will have a guarantee that we will never get more tokens than the maximum number of tokens. And then we will have 2 dropout probabilities. Honestly, I could have left it out because in this video, we will only focus on the inference mode, and the PyTorch dropout module behaves like an identity function in inference mode, so it's not really necessary, but I just decided to keep it in the code for consistency. Finally, there's this hyperparameter for the layer normalization. Internally, we will have 2 layer norm modules. We will have 1 attention module, and we will also have 1 multi-layer perceptron. we instantiate our 2 layer normalization modules. Here we instantiate the PyTorch multi-head attention module, and we feed in all the relevant hyperparameters. We could have implemented this ourselves, and actually the repo of Andrei Karpathy does contain the implementation, but I just wanted to make things minimal. But anyway, if you look at the constructor, you can see that at no point we specified the mask. We will actually need to provide the mask whenever we run the forward pass. However, our mask is not really going to change for different samples, and it's always going to be this triangular matrix representing the fact that we don't want to peek into the future. Here we just register the mask under a buffer. Yeah, and maybe let me just quickly show you what this is actually doing. So as you can see, it's basically a lower triangular matrix, and the elements that are equal to true will be those that are not going to be considered for the self-attention. And as you can see, if we provide a 2D array, which we will, it will be broadcasted across the batch. And for a binary mask, which is exactly our case, a true value indicates that the corresponding position is not allowed to attend. Finally, we prepared the multi-layer perceptron. We hardcode a couple of parameters. We use our custom Gaussian error linear unit activation and also apply a dropout. This is the input to the forward pass. It has the shape of batch size, number of tokens, and a number of embeddings. And importantly, the output has exactly the same shape, which is in many ways convenient. And here you can see the sketch of the forward pass again. First of all, we get the actual values of all 3 of the dimensions. Then we start working on the first residual block, which starts with a layer normalization. We dynamically cut off our attention mask buffer, and that is because the registered buffer actually has the maximum size of number of positions times number of positions. However, the chances are that for this given input tensor, we will have fewer tokens than the maximum number of tokens. Here we run the forward pass of the attention module. We basically provide 3 times our layer normalized tensor that will serve as the key, value, and query. And we also provide the prepared mask. And finally, we tell Torch that we don't need to have the attention weights since we are not really going to use them in this video. However, they are actually useful when it comes to trying to explain what the model was looking at and so on. And we basically take the output of the residual block, let's say, and add it to the original tensor. And here we just implement the second residual block in one line. We applied layer normalization, and then we ran the tensor through the multi-layer perceptron. And again, we added it, let's say, to the input tensor. And yeah, that's our result. And now we can just write the entire GPT module. We have seen a lot of these parameters before when we defined the decoder block, but some of them are new, and let me go through them. First of all, we have this vocabulary size, and this number represents the number of tokens we have in our vocabulary. And the reason why it's important is because we need to have this number to be able to define the token embedding, let's say, table. Number of layers will represent how many decoder blocks we will have. Internally, we will have these 2 embedding modules, token and positional. We will have a dropout module, and we will put all of the decoder blocks in the sequential module. We will also have one final layer normalization, and finally we will have the linear layer that let's say maps from the hidden embedding space to the vocabulary space. First of all, we save the number of positions internally, and the reason is that we want to check whether the number of tokens isn't too high when we run the forward pass. Here we define our two embedding modules. The first one is the token embeddings, and basically for each token in our vocabulary, we will have an embedding vector, and also we'll create the positional embeddings. The reason why we need these positional embeddings is that we want to encode some information about the position of a given token in, let's say, a given sentence. Here we define a dropout module, and as mentioned, since we're only doing inference in this video, the dropout modules will behave like identity mappings. And here, very important, we define a sequential module, which will be a list of decoder blocks. And know that these blocks are all, let's say, independent. They are separate instances. Finally, we define a layer normalization module and a linear layer that will be the very last module. So the inputs and the outputs of the forward pass are really simple. There is a single input tensor that will have a shape of batch size times number of tokens, and we'll kind of assume that each of the elements in this tensor is between 0 and the vocabulary size. And this tensor will be actually generated by our tokenizer. And note that we will actually return logits for all the tokens and not just the last one, as shown in the diagram at the beginning of the video. And also, we are not going to apply softmax inside of this forward method. We will actually do both of these operations later when we implement sampling. Here you can see again the diagram of the first part of the forward pass. Here we extract shape and device information from the input tensor. Here we just make sure that if the user tries to provide too many tokens, then we raise an exception. Here we just on the fly create a tensor that represents the position. And here we take our input token indices and we get their corresponding embeddings. Then we take the positions and get the positional embeddings, and we prepend it with an extra dimension. And that is because we actually want to element-wise sum it with the token embeddings, and we want Torch to do broadcasting over the batch dimension. And here we sum the two embeddings and we apply a dropout. Here you can see the diagram of the second part of the forward pass, and let me just repeat that we are actually going to end the forward pass after the linear module, and we will extract the last token and apply softmax in a different function. Here we run our tensor through each of the decoder blocks we have. And finally, we get our logits over all tokens in the vocabulary by applying a linear module. So in theory, I could end the video here because we implemented the forward pass. However, yeah, I thought it would be kind of boring. So what we're going to do now is that we will write a couple of utility functions to be able to copy paste weights from the Hugging Face implementation to our custom implementation. First of all, let us write a function that is going to take one tensor and copy its contents to another tensor. So in this function and also in some other functions that I'm going to write, the first parameter, or let's say the first object, is always going to be something coming from the official model. And the second parameter is going to be an object in our custom model. And we want to populate it or replace it by the values from the official object. Here we modify and place the parameter hours, and we just make sure it has the same values as the official parameter. Now, with the help of this function, we are able to copy parameters. Let's also write a utility function that's able to copy an entire decoder block that we just implemented. And And again, the first parameter is something we take from the official model. In this case, it is going to be the Hugging Face GPT-2 block instance. And we make sure that we copy all the relevant learnable parameters to our block instance. Here I just use shorter variable names to write less code. We start with the layer normalization, and it has two parameters, weight and bias. So when it comes to the attention module, we want to copy the input projection. The second learnable tensor in the attention module is the output projection, which is just the linear module again. Here we copy the parameters from the second layer normalization. When it comes to the multi-layer perceptron, we first of all copy the parameters from the first linear layer. And here we copy the parameters from the second linear layer. And yeah, that should be it. And now finally we can write a function that is going to copy all parameters of a given model. First parameter is the official object, which in this case is the GPT-2 language modeling head model. And we will try to copy all its weights to our GPT model instance. We again shorten the variable names so that we write less code. We copy, let's say, the two tables behind positional and token embeddings. We iteratively go through all the blocks and we copy them. We copy the weights of the final layer normalization module and also the head linear module, and it didn't have a bias, so we don't need to copy it. Let us now quickly check whether we can really copy an existing official model to our custom model. First of all, let us just list all the hyperparameters, or let's say keyword arguments, our GPT model needs to be instantiated. Now let us choose the model we will download from the Transformer Hub. Let's just use the vanilla GPT-2. I actually had the model downloaded already, but now we actually instantiated it. Also a small note, I set the tie word embeddings to false so that we get the same number of parameters. This is how the official config looks like. I mean, there are way more hyperparameters than we had, but the idea now would be to just extract those hyperparameters that are both in the official model, but also in our custom model. And yeah, now we actually have everything we need to instantiate our custom model. So the first sanity check we can do is to count up the number of parameters in our model versus the official model. Our model has 163 million parameters, and the official one has exactly the same number of parameters, which is good news. Let's set both of the models to the evaluation mode because we will be running the forward pass and we want to make sure that things like dropout are deactivated. And now we don't even want to take real text and tokenize it. We can just generate some dummy indices and pretend they correspond to some tokens. Let's try to get logits from both our model and the official one. So first of all, we can see that the shape of the logits is identical for both the official and our model. We can see that we have a single sample in the batch. Then we have 4 tokens that we provided. And then the last dimension represents the vocabulary size. But what about the actual values of these tensors? Are they the same? The answer is no. And let us actually inspect what the biggest difference was. The biggest per element difference was 13. I mean, this is not surprising because we randomly initialized our model and we took a pre-trained model from the transformer hub. What we want now for this to work is to use our copy model helper function that we just implemented and make sure that the trainable weights of our model are identical to the trainable weights of the official model. So the weights are copied, and let us rerun the same checks. We compute the logits. I mean, we did not have to recompute the official logits because we did not modify the official model, but whatever. And as you can see, these two tensors are virtually identical. There are some small differences. I did not really investigate too much where they come from, but yeah. And as you can see, the biggest element-wise difference is extremely small. Okay, so we verified that the copying works and we will use it later. Let us now investigate how one can take the logits that are the output of our model and use them to generate a new token. As you saw, the forward pass outputs a tensor of logits, and one can just simply run it through a softmax layer and get a probability distribution and then sample from it. However, there are multiple ways how to extend this approach to be able to control the generation process a little bit more. I will talk about applying a temperature and only considering top K elements. However, know that there are other techniques that are often applied when generating tokens like beam search, but I'm not going to talk about them. Okay, so first of all, here you can see a formula of the softmax with temperature, and note that it is nothing else than a standard softmax. However, the logits we feed as input will be divided by a constant that is called the temperature. And what's interesting is that if the temperature is 1, we end up with the standard softmax. The second scheme that we will implement is a so-called top K, and it is extremely simple since we only consider the top K tokens with the highest probability, and we make sure that the probability of remaining tokens is 0. I prepared a small visualization to demonstrate how these two schemes influence the original probability distribution. I'm not going to talk about the implementation since we are going to implement both of these techniques in a few moments. So what you see on the left is, let's say, the original distribution, and the thing on the right is a modified distribution. For now, they are identical because the temperature is 1 and the top K is, let's say, larger than the number of tokens we have. Let us increase the temperature to see what happens. The distribution is getting closer and closer to a uniform distribution. One important implication of this is that if we sample from this higher temperature distribution, we would expect the variability of samples to be high. What if we decrease the value of the temperature below 1? In a way, we sharpen the distribution and the gap between low probability and high probability tokens is increasing. In our token sampling context, this can be useful to make sure that our model only sticks to the most probable tokens. And we see that for very low temperature values, we basically end up with a distribution where the original argmax token has close to 100% probability. Let us also quickly look at the top K hyperparameter. In this specific example, our vocabulary consists of 8 tokens, and if the top K is higher, then this basically means that we are considering all tokens. However, let's try to make it lower than 8. And we see that only the most probable tokens survive and the rest of the tokens is assigned a 0 probability. And in our context, it might be used to make sure that the model always goes for the most relevant tokens while not modifying their relative probabilities too much. Finally, let me just stress that even after applying both of the described techniques, the probabilities will always sum up to 1, and also the argmax token will stay the same. Alright, so let us now just implement this function that is able to generate the next token given some initial sequence of tokens. First of all, we provide our model instance. Then we provide a list of indices representing tokens that we are going to condition on, or in other words, this would be the input text. Here we have the temperature hyperparameter. Here we have a sample flag. If it's active, it means that we are going to be sampling, which means that inherently there will be randomness. However, if it's set to false, we will just always take the argmax. Top K parameter, if it's none, then we don't modify the distribution at all. However, if it's a number, an integer, we only keep the top K most probable outcomes. And finally, the only thing we return is the index of our new token. So here we just make sure that we only include the tokens that were, let's say, in our context window. So let's say if the user provided too many tokens that our model wouldn't be able to digest, we just take the number of positions, most recent ones. And here we take the list of tokens and cast it to a torch tensor. And we also prepend it with a dummy batch dimension. We run the forward pass on our model and we get the logits. However, what's important is that we take only the first sample because our batch was composed only of the first sample. And also we take the very last token, or let's say the embedding corresponding to the very last token, and throw away all the remaining token embeddings. And here we just divide by the temperature. So let's say if we want to apply this top K clipping, then first of all, we find the top K biggest elements inside of our logits tensor. And then we simply take the smallest of the top K values and we make sure that all the elements that are actually lower than this value will be set to minus infinity. And if you're wondering why minus infinity, the reason is that in a couple of seconds, we will actually take this logits tensor and we will run it through the softmax activation. And after softmax, all of these minus infinity logits will actually end up having exactly 0 probability. This is where we create the probabilities. And yeah, if we want to have randomness, we sample, and internally this is done through the multinomial distribution in Torch. However, if we don't want to sample and don't want to have any randomness, we just take the argmax, which would correspond to the token with the highest probability. Then yeah, we just extract the actual integer and return it. And yeah, we're done. Then now we just want to write a small command line interface that will do two things. First of all, it will do the copying that I demonstrated in the IPython session, but also it will allow us to generate text using this generate token utility function that we just wrote. Here we configure logging, and the reason why we want to use logging is to be able to monitor the timings of the new token generation. And now we just want to write the CLI parser. Let me go through some of the arguments. Here we can specify the model name, and there are 4 options. All of these models can be downloaded from the Hugging Face hub. The user is supposed to specify some initial text. This parameter, we've seen it before. It just represents whether we want to sample randomly, and if not, we will just take the argmax. This steps argument is an interesting one because the generate token function only generates 1 token at a time. However, here we will also build a logic that kind of iteratively calls this generate token function, and the number of steps represents the number of tokens that we are going to generate. And yeah, these 2 parameters, we've already seen them. We just let the user choose the verbosity. And we instantiate a tokenizer that corresponds to the model that we selected. Here we instantiate and possibly download the model. We list all parameters that the constructor of our GPT model needs, and we find the corresponding value in the config of the official model. We instantiate our model using these hyperparameters, and we also set it to the evaluation mode. We copy all the trainable weights from the official model to our custom model. We use the tokenizer to actually take our initial text and convert it to a sequence of token indices. If the user wants, we also set a random state, and it will matter when we call the generate token function because there could be sampling happening inside. We have a for loop whose goal is to generate multiple tokens. First of all, we generate a single token and we provide all the relevant hyperparameters. Then we use this auto regression trick where we just take the new token that we just generated and we add it to the end of the input sequence. Once we are done with this auto regression loop, we just ask the tokenizer to decode the token indices back to human readable text. And we just print it out to see what the result was. And yeah, our CLI is ready to be used. So we have written our small entry point, and now we would like to see whether it's able to generate some nice text. So first of all, we make it verbose. We set the number of steps to 80. Then we choose the GPT-2 model, but as you saw, there are different ones. I have this one downloaded, so we'll just stick to it. And the second positional argument should be the input text. So let me just stress that since we did not supply this sample flag, we will always just take the argmax, which is the most likely token, and therefore there shouldn't be any randomness. As you can see, it's literally just repeating the sentence we gave it, which is not something we want. And the reason why this is happening is because we did not sample, we just went for the most likely option. And in this case, it seems to be repeating the same text again and again. So yeah, let's add sampling. As soon as we add sampling, it will be also nice to set a random state so that we can get reproducible results. I set it to 2, and yeah, let's run it again. As we can see, it actually generated some text. However, as you would probably agree, it quickly changed the topic and then just started rambling about something. The problem this time is that even though we are sampling, it can totally happen that every now and then we select a token that has a relatively low probability. And let's say this completely distracts the model and leads it to change the topic. And we can actually fix this by only sampling from the top most likely tokens. So I guess this time it stayed on the topic. One can argue that it's kind of repeating itself. At the same time, the initial text that I came up with is very basic, and maybe the GPT model just tries to replicate its style. Let's try a different random state. Yeah, the start was pretty good. Then it again started repeating itself. Let's maybe make the top K a little bit larger. Let's go maybe back to 5, but try a different random state. Yeah, I guess it works. And let me also show you what happens when we provide extreme values of the temperature. Let's get rid of this stop K for now. And let's set the temperature to 0.01. And by the way, when we did not provide it specifically, the default was 1. And as you can see, it repeats the same thing again, which is exactly what was happening when we were just choosing the argmax. Because even though we are sampling, we are sharpening the distribution so much with this low temperature that this argmax token has an extremely high probability, whereas all the remaining tokens have a very low probability. And let us now do the other extreme, where we set the temperature to 20. And as you can see, it generates random tokens. And that is because by providing such a huge temperature, we turn the distribution into something that's very close to a uniform distribution, which means that all of the tokens in the vocabulary will have more or less the same probability. And finally, let me also show you what happens when we want to generate a lot of tokens. Here, instead of 80 steps, we want to generate 800 steps. And as you can see, the initial steps are done really quickly, but then we are slowing down. And the reason why it's slowing down is that our context gets bigger and bigger, which in turn means that the number of tokens that enter the GPT model gets bigger and bigger, which leads to slower inference. This given model allows for the context of around 1000 tokens, which was dictated by the number of positions hyperparameter. Let me point out one interesting and important thing, and that is that the amount of time it takes to do the inference is quadratic in the number of tokens. And the reason is that the GPT model has a bunch of self-attention layers inside. To illustrate this point, I ran the CLI for even more steps and then generated the following plot. On the x-axis, we see the steps, and on the y-axis, we see how many seconds it took. The red line represents the actual times, whereas the green line and the blue line represent the best linear and quadratic approximations. And clearly, we see that indeed the time complexity of the inference is quadratic. Finally, around the 1000th step, the curve becomes constant, and that is simply because we only consider the 1024 most recent tokens, and the older ones are discarded as you saw in the implementation. Anyway, that's it for today. I hope you enjoyed the video. Feel free to write any feedback in the comments below, and if you want to see similar content like this, definitely make sure to check out some of my other videos or to subscribe. Have a nice rest of the day and see you next time.